Space is vast. It's filled with stars, planets, and galaxies. But there's something else out there, something we can't see. It's called dark matter, and it's one of the biggest mysteries in the universe. Imagine a detective story on a cosmic scale. We see the clues, but the culprit remains elusive. Dark matter doesn't emit light, it doesn't reflect light, it doesn't absorb light, it's completely invisible to our telescopes. So how do we know it's even there? Because it interacts with the universe through a fundamental force, gravity. Everything we can see in the universe, stars, planets, gas, dust, is made up of ordinary matter. This matter makes up everything we interact with in our daily lives. But here's the catch: ordinary matter only accounts for about 5% of the universe's total mass and energy. The rest is dark matter and dark energy. Dark matter is different. It doesn't interact with light or other forms of electromagnetic radiation. This makes it invisible to us. It's like trying to see a black cat in a dark room without a flashlight. The story of dark matter began in the 1930s with Fritz Zwicky. He was studying the Coma cluster, a massive group of galaxies. Zwicky noticed something strange. The galaxies were moving much faster than they should have been based on the visible matter alone. He calculated that there must be much more mass holding the cluster together than he could see. He called this missing mass Dunkel Materie German for dark matter. His observations were met with skepticism at first, but subsequent observations of other galaxy clusters confirmed his findings. Fast forward to the 1970s, a time of great scientific curiosity and exploration. Astronomer Vera Rubin was deeply engrossed in studying the rotation of spiral galaxies, a task that required meticulous observation and analysis. Through her detailed observation, she found that the stars in these galaxies were moving much faster than what the existing theories predicted. Surprisingly, the stars on the outer edges of these galaxies were orbiting at nearly the same speed as those closer to the center, defying the expected decrease in velocity. This unexpected finding contradicted the well-established laws of physics, as we understood them at the time, causing a significant stir in the scientific community. According to the known laws of physics, if the visible matter was all there was, the outer stars should have been flung out into space due to insufficient gravitational pull. The only plausible explanation for this anomaly was the presence of a halo of invisible matter, known as dark matter, which provided the extra gravitational force needed to keep the galaxies intact. Rubin's groundbreaking work laid the foundation for the concept of dark matter, revolutionizing our understanding of the universe and its unseen forces. Today, the study of dark matter continues to be a major focus in astrophysics, as scientists strive to uncover more about this mysterious substance that makes up a significant portion of the universe. The quest to understand dark matter not only helps us comprehend the structure and behavior of galaxies, but also brings us closer to unraveling the fundamental mysteries of the cosmos. As we gaze into the night sky, we are reminded of the unseen forces at play, shaping the universe in ways we are only beginning to understand. Section 5. The Puppet Master. Think of a trampoline. If you place a bowling ball in the center, it creates a dip. Now if you roll a marble across the trampoline, its path will curve around the bowling ball due to the dip in the fabric. Dark matter acts like the bowling ball, creating a gravitational dip in the fabric of space-time. Galaxies, like the marbles, move within this warped space-time, influenced by the invisible hand of dark matter. This is how dark matter shapes the universe, even though we can't see it directly. Section 6. Bending the fabric of space. One of the most compelling pieces of evidence for dark matter comes from a phenomenon called gravitational lensing. This fascinating effect occurs when the gravitational field of a massive object, such as a galaxy cluster, warps the fabric of space-time itself. Imagine a distant galaxy as a flashlight beam shining across the universe. The light from this galaxy travels through the vast expanse of space, encountering various cosmic structures along its journey. If a massive object like a cluster of galaxies containing dark matter lies between us and the distant galaxy, its gravity can bend the light from that galaxy. This bending of light is not just a simple deflection, it is a profound warping of space-time, causing the light to follow a curved path. This bending acts like a cosmic magnifying glass, distorting and brightening the image of the distant galaxy. The effect can create multiple images of the same galaxy, arcs, or even rings of light, known as Einstein rings, named after the physicist who predicted this phenomenon. Astronomers can analyze these distortions to map the distribution of dark matter within the intervening cluster. By studying the way light is bent, they can infer the presence and amount of dark matter which does not emit, absorb, or reflect light, making it invisible to traditional telescopes. This method provides a powerful tool for understanding the unseen mass that makes up a significant portion of our universe. Section 7. Galactic Architects. In this chapter, we delve into the cosmic forces that shape the universe, focusing on the mysterious and essential role of dark matter. Dark matter played a crucial role in the formation of the universe as we know it. Without it, the universe would look vastly different, and the galaxies, stars, and planets we see today might not exist. In the early universe after the Big Bang, everything was a hot, dense soup of particles. This primordial state was chaotic and incredibly energetic, with particles constantly colliding and interacting. Gravity caused these particles to clump together, but ordinary matter alone couldn't clump fast enough to form galaxies in the time available. The gravitational pull of ordinary matter was simply not strong enough to overcome the rapid expansion of the universe. This is where dark matter comes in. Unlike ordinary matter, dark matter doesn't interact with electromagnetic forces, meaning it doesn't emit, absorb, or reflect light, making it invisible and detectable only through its gravitational effects. Because it doesn't interact with light, it wasn't slowed down by the radiation that permeated the early universe. This allowed dark matter to move freely and form structures more quickly than ordinary matter could. Dark matter clumped together first, forming a gravitational scaffolding that drew in ordinary matter. These dark matter clumps acted as seeds around which galaxies could form, providing the necessary gravitational pull to gather ordinary matter. This accelerated the formation of galaxies, including our own Milky Way. Without the influence of dark matter, the universe would be a much darker and emptier place, devoid of the complex structures we observe today. The interplay between dark matter and ordinary matter is a fundamental aspect of cosmic architecture, shaping the universe from its earliest moments to the present day. Section 8. The Hunt for the Invisible. Scientists around the world are actively searching for dark matter. They're building ultra-sensitive detectors buried deep underground, hoping to catch a glimpse of these elusive particles as they pass through the Earth. They're also smashing particles together at near-light speed in particle accelerators, looking for new particles that could be dark matter candidates. The search is challenging, but the stakes are high. Identifying the nature of dark matter would revolutionize our understanding of particle physics and the fundamental laws of the universe. Section 9. Dark matter versus dark energy. Dark matter isn't the only cosmic mystery out there. There's also dark energy, a completely different and even more perplexing phenomenon in the cosmos. While dark matter pulls things together through gravity, dark energy pushes things apart, causing the expansion of the universe to accelerate. Think of dark energy as the opposite of gravity, a kind of anti-gravity that's pushing everything in the universe farther and farther apart. The nature of dark energy is one of the biggest unsolved problems in modern physics today. Section 10. Unlocking the universe's secrets. The quest to understand dark matter is a journey into the unknown. It's a testament to human curiosity and our desire to comprehend the vast and mysterious universe we inhabit. The universe is full of surprises. Each discovery brings us closer to understanding the fundamental nature of reality itself. So the next time you look up at the night sky, remember that there's more out there than meets the eye. The universe is full of hidden wonders, and the discovery of dark matter is just the beginning.